Good evening, everyone. Welcome back to the data science program. In the previous session, we were looking at the boosting algorithms that are supported uh, under the hood of machine learning. And in the today's session, we will be looking at the programming version of the same thing, right? So let's quickly try to look at what was the boosting algorithm. So it's actually an ensemble method that basically creates a strong learning model from a lot of other algorithms, what we call as weak learners. So in order to create a ensemble method, right, we build the model by training the data, creating a second model that attempts to correct the errors from the first model, right? And models are added until the training set is predicted perfectly, or maximum number of models that are allowed to include, right? So once that are completed, you can say that you're going to end up the process. So that is what is going to happen in the boosting algorithms. So, and inside the boosting algorithm, if you remember, we have seen what is called as adaptive boosting algorithm. That is one of the way to add a new predictor to correct uh, the predecessor to pay a bit more attention to the training instances than the previous one. So previous one may have done some mistakes. You will try to correct that, right? So that is what happens inside the ADABOOST. And we have discussed about the gradient boosting. That is also another leading ensemble algorithm, and it uses the gradient descent method to optimize the loss functions. So we basically have seen a lot of what you call uh, the theoretical aspects have already been discussed. Now we'll directly jump into uh, the programming aspect of that. So as a first step, let us try to import the various packages. So let me bring in the numpy np import pandas as pd, matplotlib dot pyplot as the plt. Okay, and we'll also bring in let us say the seaborn as sns. All right, then I want to import so let's bring in the various regression on the SVM for various types of not only just SVM. We'll bring in the scalars, encoders, etc. So first, let me bring in the support vector regressor for this. Okay, SVM import the SVR from sklearn dot linear model import the ridge as well as the lasso. Anyway, we have seen the lasso and the ridge right? What they are. It's again a part of a linear model, right? Then sklearn dot preprocessing, import the standard scaler, and also you have to import the label encoder. Okay, so these are I'm going to import from this. Then let me bring the various methods that are required for modeling our data. So I'll try to import them from sklearn dot the model selection. Okay, from the model selection you need to import the train. Meanwhile, let me connect to a resource. All right, connect to a CPU. Meanwhile, while I type this, okay, so train test split. Okay, I want this. Then from sklearn dot sklearn dot model selection, I want to import. So there is a particular method that actually performs repeated stratification. So yeah, so you can see that it suggests this one. I also want to sklearn dot model selection. We import sorry, what happened? Model selection. Okay, let me try to import the cross validation, right? For performing the cross validation we need cross val score. All right, so these are the various methods I want to bring in from for the data modeling process. Then let's try to bring in something that are required for our models performance evaluation. All right, so if you want to do that, we already have seen this from sklearn. Directly you can import what is called as metrics. All right, now what else we need? We need, since it is a boosting algorithm, we need various weak learners. So when I say weak learners, you understand that we are going to bring in the various algorithms, ADABOOST, gradient boost, random forest, stacking algorithms, etc. are supposed to be brought from the ensemble. So sklearn.ensemble import. Let's bring in one by one. ADABOOST classifier is the first one which I want to bring in. Ensemble import. We need the gradient boost. Let me bring in the regressor first. Okay, as the name suggests, I brought in gradient boosting regressor. All right. sklearn dot ensemble import random forest. I'll bring in. Also, I'll bring the stacking. So that's also present inside sklearn dot ensemble import stacking regressor. All right, that is done. Then we have a tree. So we need a tree algorithm. So decision tree classifier is definitely required. So let me bring in that from sklearn.tree. We can import decision tree classifier. Okay. From sklearn.tree, you need to import the plotting. There is something called as plot tree. Yeah, it suggests the same. All right. And from, let me try to bring in the XGBoost. From XGBoost, yeah, from XGBoost import XGB. Do we have regressor? Yeah, so I'll bring in that first. Then let me import XGBoost as XGB. Sorry, spelling mistake. XGBoost. All right, as XGB, and I'll import the graphical visualization graph viz. Okay. Let me check what else we need. I think everything what is required for our coding we have imported. Let me try to turn off some warnings. All right. Import warnings and warnings dot filter warnings. You can simply say that ignore all the warnings which are under the category called as right simple warnings, not an errors, right? We would like to say that ignore them. Okay, then let us do one thing. I think I need to bring in the data set as well, right? So let's take up the data set from the existing that sklearn itself. All right, so what I do, I'll go to the next line and I'll try to import the data set from the sklearn itself. From sklearn.datasets import load boost. All right, so let's try to run this part, and as you can see, so for one of the example, I need this data set. So that's why I actually am bringing the load booster as well. All right. All right. Everybody, please check your the chat box once. I'm going to add one file over there. All right. So that's the first file which we will be using now. Okay. For the first part of the hands-on, you will be using this data set. Please give me 1 second, 1 minute. I'll try to add it to the chat box. Everybody can download it from the chat box and you can use it. So you can see here, this is Indian liver patient.csv. This is the file which I'm going to use. I also have added the same thing to the chat box. Everybody can download from it. Okay, I'll give you 2 minutes of time to do this, right? Get this, and meanwhile, I'll just type the next sentence. Okay, next code. So I'll create a data frame out of it, but I'll wait after running this. I'll wait for say 2 minutes. So as you can see here, uh, we are using the read CSV to read the CSV file, and this file actually consists of the following data. All right, so age, gender, and 1, 2, 3, 4, 5, 6, 7, 8. So some 8 or 9 various columns present over there. So that's what is the patient data set related to the liver. All right, so download and upload that to your Google Colab by using this file, this link. Upload a particular session storage, right, using this one. And once that comes over here, then you can type these two and execute the part of it. So once it is done, now our intention is to do the pre-processing of this data. So we need to have a very clear look at what is this data, right? How this data looks like. So if you remember the pre-processing steps that are supposed to be included, first we need to check that whether there are any missing values. So let's do that now. ds dot is null, and I'll ask for the sum. It says that, yeah, among these you don't have, but this particular column has 4, right? So what you can say that you can drop, create a new this thing. So df1 is equal to df dot drop any is a function, if you remember, and then I'll check that df1. In df1, do you have any is null present? It says false. Okay, so most of the time we have only the not a null. You can simply check that, right, if there is a null or not using this method directly. But the one of the more sophisticated way to check the attributes and their correlation between each other is by using by bringing up the correlation matrix. All right, so let's try to bring that as a heat map using the Seaborn. All right, so let me create that first. So big size equal to, let's try to define it say 10 comma 10. I'll modify this if the size becomes larger or smaller than expected. Then I'll go to SNS dot heat map. I'll use the absolute value of the df1 dot correlation. Then there is an annotation option. I'll say that this is equal to true. I want the annotation. Then do you need a square? So you have an option to enter that. Square plots, right? So square equal to true. See, all these are options, right? You can use it if required. I'm showing the various options here, right? Then do you want to see a color bar? You can use it. I will say false. I don't want to see. What is AX? It's the AX itself. Then you can specify line width equal to, maybe keep a smaller value like 0.25 or something. Okay, let's see. Okay, I can see that it's slightly larger on my screen, right? It actually extends to the right. So what I do, I'll try to reduce the size to 8 cross 8. Let me run that. I'm looking for something which fits my screen. Yeah, so now this is much better. So brighter the color, you can see that there is more and more correlation. Okay, and the darker the color, it means the numbers read lesser and lesser, so it means they have very lesser these things. Okay, so I can see let's try to remove the rows or columns that do not contain the required or higher, that do not show very high, what you call, correlation between others. So I can see that the direct, okay, let me see this one. Then this one, because other one shows the similar this thing, so I don't have to keep the one of them. So these two, right, total and the direct, I can remove one of them, and out of these two I can remove one of them, and the total and this second one. So total proteins I can try to remember. So three of them I will remember. I'll remove. Okay, so why I am removing? Because, right, they're not showing the uh, there is one or other columns which are similar to this, so I can simply remove them. All right, so df2 is equal to df1 dot drop. Let me try to drop the following. So you can simply specify what are the columns. Columns equal to, you just have to enter it as an array, list. So the direct, okay, let me look at the spelling and write it properly. Direct underscore, will it suggest? Let me check so that I don't make a mistake. BILIU. Okay, so this is the one. Then second one, I just want to remove AMINOPRAS. I guess so. Let's see. Correct me if the spelling is a mistake. Okay, if there is any spelling mistake. And the third one is total PROTIENS. Okay, let's see. There's a spelling mistake. Okay, so it should be total. Fine. Okay, now as we have seen earlier in this data set, we have dropped three of the columns, and only one column, which is the gender, which is a categorical type. All the remaining data are continuous data. All right, fine. Now let's modify them as well. So df2, let's look at the df2 of data set. It's 1 2 1 2, right? So this is what we have it. So there are two different categories, right? 1 and 2, right? So what we try to do here, df data set is equal to, I'll replace 1 by 0 and the 2 by 1. Okay, so that is df2 dot the data set, and in the data set dot replace 1 by 0. This is what I'm saying. And also in the df2 a column called data set. I want to do the following. There is no okay. So df2 data set replace. You can see that I replace 1 by 0. I can do 2 by 1. Okay, you can simply verify that now once again by using the same df2 data set. So you just have now sorry, ones and zeros. So we just have the ones and zeros present over there. So let us try to look at the various categories of the data, right? How many people have the disease? How many people have participated in this whole study, right? Let's try to get another picture of that data. All right. So let me try to print how many people have the disease. Okay, so how many people have the disease? How do you want to find out? It's actually has to go to, we need to group by gender, and we need to go to the data set, and we need to take the sum. So data set means data set is 1 means they have disease, data set is 0 means they don't have a disease. All right, so that is one. Then if I take a count, if I use a count, it actually gives you the complete out of the complete data set, how many are male, how many are female. That's actually going to give you what is called as the number of people who participated in this particular study. So that's how we will visualize this. So what I do, I'll go to \n. That's a new line character. Then I'll do this df2 dot group by, according to what you want to group by, according to the gender column of this data set. All right, then specifically I want to look at the data set. All right, dot sum. Right, take a sum, then give a new line character. Okay, \n. Similarly, I also want to print how many people have participated in the study. This is what I want to find out now. So I'll go to a new line once again. Now you try to print out along with this the df2 dot group by. Once again, go to the column according to the gender. Data set. Count. All right, so count, I'll go to the new line, backslash n. All right, so let's try to see. Yeah. So among the data set, it's how many people have disease, right? 49 female and 116 male patients have the disease. Okay, and just to visualize the participation, normally participation will be larger than the ones having the disease, right? So you can see that female 140, male 439. So this is the study. Okay, so that's one way of visualization. Now I want you to write a code to get me. Okay, I'll give some time for you to do this, but this is what I want to print. Print percentage of people disease, percentage of people with disease depending upon gender, right? You just have to show that percentage wise, out of female it's like 49 by 140 and 116 by 439. So that's what is required. You can see here it's out of 140 female, right? 49 of them have the disease. Out of 439 males, you know that 116 have the disease. So but you don't have to uh, right, do this calculation right now, because this may change for a data set. So how do you do this in general is what I want you to show me that. Okay, so I'll give say 1 minute of time. Okay, so write your answer in the chat box. I can see that and we can have a discussion about it. Okay, so I think many of you have given the answers, right, which are pretty much close. Just compare your answers with my answer. So df2 dot group by, definitely it has to be according to the gender. It's a gender, it's a column over here, and I have to say specify which is the particular columns values we are going to look at. So that is the data set column, and I need to take the sum dot. Okay, so this has to be divided by the total counts, correct? So you can see that above that we have a count, right, that is written. So I just have to divide them and separate it. So divide by df2 group by the gender for the data set dot count. Just run this and see. It says what percentage. So anyway, definitely you can multiply by 100. All right. So I'll just say into 100. So what's the insight that you can get from this? So women have higher percentage of the disease, right? Okay, so let's try to define the x and y variables. So x is equal to, from this particular data frame, I'll say, okay, use the gender, every column, right? Every column which is not a y value, right, will become a x value, will become a feature in our data set. All right. So that's why. So I have total EILI. All right. Then I have another one, alkaline. It's capital. Okay. Then my fourth column, column number 5, and the column number 6 is all right. So this will be the x, and I also create a y. So y is equal to df2. Is it df2? Okay, it's not a data frame. Actually, I need a panda series, right? So first, let's create a pd dot series of the df2 data set. All right, so we have x and y. Oh, let me check. Panda series is, oh, sorry about that. It should be capital. Okay, fine. Now, the gender column, whichever we have, right? It's actually, it's a categorical data. So I need a numbers to be present over there instead of male and female, right? So what we can do here, we can, okay, let's create a label encoder is equal to, it's a label encoder in my x data, that is in the x gender is equal to label encoder dot fit transform. X gender, right? So that the X column becomes equal to or every entry in X becomes a number now. All right, so then I go for X train, X test, Y train, Y test will be equal to train test split. I need to pass X. I have to pass what is the Y? I will say test size. Say 0.2. Then random state is equal to given number. All right, then we'll use a scalar over here. So scalar is equal to standard scalar. This needs to be applied on the exit train as well as the X test. Exit train is equal to the scalar which you have defined now, dot fit transform. Scalar dot fit transform on the X train. You will do the same thing on the X test as well. Is equal to scalar dot, now you don't have to fit, you simply transform. Okay, fitting already has happened, you don't have to fit again. Simply do this on the X. Okay, let's run this. That is done. Right now, so the data set is ready with us now, and now we can directly perform the ADABOOST classifier. All right, so let me start with the ADABOOST. So I'll call it as ADB, as it's an instance of the ADABOOST classifier. ADABOOST classifier. Right, ADABOOST classifier needs multiple weak learners. All the weak learners will try to implement using a decision tree. Okay, that's what we had studied. We had discussed in the theory part, right? So if you want to recall the basics of the decision tree classifier and the ADABOOST classifier, you can refer the previous previous lectures on the same series. All right, where you will find out the complete details. Okay, and okay, let me define decision tree classifier. So you can definitely specify what is the depth required, right? So let me define, it's one of the hyperparameters. Okay, depth equal to, let me keep it 2. If it does not perform well, definitely I'll change this. Okay, so max depth equal to 2, and then the number of estimators, n estimators equal to maybe 150. Let's see with this number, and the learning rate, want to start with say 0.5 maybe. The random state, let's keep it 100. Right, then ADB dot fit X train, comma, Y train, So let's try to fit this. All right. It might take some time, but sure. So we have the result. Now what we do, we will perform the repeated k-fold cross validation, because it's going to provide you a way to improve the estimated performance of this particular model, right? So you remember the concept of cross validation, which was discussed in the very first session of our machine learning concept. Okay, you can go back and you can try to recall that. So this whole repeated k-fold cross validation, it repeats the cross validation procedure multiple times, and it will report the mean result across all folds of all runs, right? So expected value is more accurate than some unknown performance measure. All right, so that's why we will be looking at that. All right, so let's first let me bring that in. All right, so I call it as CV. That's a cross validation. Repeated, already we have. Okay, repeated stratified k-fold. I'll just say that number of splits n underscore splits. Let me say that is equal to 5. N repeats, number of times you want to repeat, I'll keep that also, say 5. And okay, so let me bring this to a new line. Random stage is equal to, all right, so let's do this. All right, now I want to visualize. Okay, so the cross validation score is what I want to see, right? So how good is my model? I just want to verify that. So I'll say n underscore scores is equal to cross val score of which model? ADB. Okay, using x as your input data, y as your the labels. The scoring should be happening by means of say accuracy, CV is equal to the CV which we have defined or used just now, and use all the computing power what you have. Okay, n jobs equal to -1. Use the complete computing power what you have in terms of the number of processors you have in your system, and error score is equal to race. Right, let me try to once this is done, I'll directly try to print out print accuracy percentage 0.3f np dot mean of n scores, whatever n scores we have, I need to multiply that with 100 into 100. All right, 68.87. Okay, now the next objective is to visualize this the classification and its error by looking at what is called as a confusion matrix. That's going to help us in understanding where the misclassification is happening, right? So let's bring that into picture. Labels equal to ADB dot predict of the X task, and matrix is equal to matrix dot the confusion matrix, matrix dot confusion matrix of. So how do you get the confusion matrix? You need to use a Y test and compare it with the labels, right? So because the labels are something you obtain by the classification of the test data, it machine says that they are labels, but actual data is Y test, right? So by comparing these two, you can get this. And I'll go to the I'll try to visualize the this using a heat map. So in the next step, SNS dot heat map. All right, we have the matrix, and I need square equal to true. Annotation is required, and I'll use a format that is equal to D, and color bar I don't want to see, so I'll say false. Then in the plot, go for X label. It's a truth. Y label. Prediction. Mistake. All right, let's see what's happening now. Okay, so from this we can say that 61 of no disease and the 13 of with the disease have been classified correctly, right? And as we know, there is the AUC ROC method to identify the correctness of our what do you call the modeling, correct? So for the model, you need to plot the AUC ROC. That's also a highly recommended method to visualize this. So okay, so if the what do you call the area under the curve becomes equal to closer to 1, it's a good model. So we expect this model to be good, and since our prediction rate is pretty close to not close to 1, sorry, I don't expect the area to be 1. Okay, I expect the area closer to 0.5 or something, right? So let's see how what we get here. All right, so the logic ROC AUC is equal to, from the matrix dot, I'll get the, I think we have this ROC should be suggested. Let's see. Yeah, ROC AUC score. Again, you need to get this by comparing the Y test with the model's prediction, that is labels. Okay, yeah. We get this. Then the false positive rates, true positive rates, the thresholds, etc. we can directly obtain once again from this. Right, so I'll call it as FPR, false positive rates. So the true positive rates, TPR, and threshold I got as a SHOLDS equal to the matrix dot ROC curve. Yeah. Of, I just have to mention what are the various parameters which I want to pass here. So to this, I want to pass, the first thing is the Y test. Then I'll pass the ADB dot predict the probabilities. X test. All the rows, first column. Okay, so this is what I have to pass as a parameter. Then now we calculate this and we'll move ahead to, we'll go to the plotting part. All right, so go to the figure and I'll call a plot, right? Plot will be always the false positive rates versus the true positive rates. You need to say that what's the label that you want to give is equal to yeah, let me put it in this way. This is area equal to, let me format this in the following way: 0.2, two decimal places, okay, of a floating point number. Then percentage and logit underscore ROC okay. I just want to remove this. All right, so anyway, we don't need this. Like this. Then so we can go with the legend ELT legend and give a location that is equal to lower right. You will see the legend over there. Then show the plot. Or if we want to see the what do you call, the 45-degree line connecting from 0, 0 to 1, 1, I can actually, normally that is also shown as a standard graph. Okay, so standard part of the graph. So I can do that. So plt dot plot, right? You just have to mention the 2 points which you want to connect. Okay, so can write 0, 1, 0, 1. It means 0, 0 to 1, 1. I'm trying to connect. Format is red dash dash. Okay, let's try to see that. Yeah, so this is how it looks like. So 0.56 is the area. Closer to 1, this means it's a good one. So we need to, right, check or visualize the performance of a multi-class classification problem. Normally we use this area under the curve, right, of the ROC curve. Okay, right. So this is what is the implementation of the first boosting technique. All right, so that is the ADABOOST classifier. Okay, let me know if you have any doubt on this. Otherwise, we'll be moving further to the next implementation. So that is the gradient boosting implementation. Okay, let me just add a text over here. So here we'll be implementing the gradient boosting, and I'll also mark somewhere here. This is okay. So that is ADABOOST implementation. Boosting is not required. I'll correct that. ADABOOST implementation starts here, and that's what we have completed so far. So the next objective is to move ahead to the next boosting, that is called as a gradient boosting. Okay. So in case of the gradient boosting, let's bring in the data set first, right? So anyway, we know that this is a regression data set related problem. So we have to bring what you call as a regression data set for this purpose. So first let's try to load the data. Boson is equal to, it's a load boson. We already have already brought this. Okay, it's there in our memory, right? So we can directly use it. Then let's see what we have here. The boson dot keys Okay, so it's a dictionary, so you can see that these are the various keys we have: data, target, feature names, file names, etc. Right? And I will see print boson dot data dot shape. Let me check. Yeah. All right. So 506, 13. So it means there are 503, 506 rows and 13 columns. Right. So let's look at what are these 13 columns, what these columns have been named, or right. We'll try to look at that. Boston dot, yeah, feature names. You can call it like this. So as you can see, we have the following names given to 13 different. All right. So first, let's try to create a data frame. So df is equal to pd dot data frame. What's the name of this data? Boston dot data, and I need to specify what are the columns. All right. So df dot columns equal to Boston dot feature names. All right. So there has to be a data frame with the name of each of the column denoted by the feature names of this data set. All right. So let's visualize that. Df dot head, say 10. Okay. Right. Similarly, the df dot tail. Right. Okay. Last 5 entries. You can see like this. Right. Now we need to predict the price. So it's a regression problem, but there is no price that is present over here, right? Because that is actually kept it inside a completely different attribute inside this data set. It is called as a target. Okay. So what I try to do here now, I'll try to append that column to this data frame. All right. So I'll create a new column called price. That should be the BOSTON dot target. So inside this data set, we have right made this. So what I try to do now once again I'll check this. All right. So df dot head. So I should be having another column called price. Yes, you can see here the price has been added up together. Right. Earlier it was not there. And I can also check the info. If you want, you can check the df dot info to find out some of the information about what type of how many entries are there, what is the data type, etc. We can directly come to know about this. Okay, let's separate out the x and y variables now. X comma y is equal to, I use a I lock because I know the index value. All right, so I know that for x it's all the rows and everything excluding the -1 column. Okay, so that is the x value, and the y value is nothing but from the df I know the location, so I log all the rows of a specific column, and the column number is -1, the last one. Okay, so this is how we have x and y. All right, so x string, x test, y train, y test to be equal to train test split. We need to split them. Okay, so split according to this x, the y, then test size equal to 2, random state equal to 100. Okay, so now we need the gradient boosting, right? Model to be defined. So let's try to define two different models, one with the default regression parameters, and the second one with the some of the parameters which we can define. Okay, we define something, we change the parameters, and one more model which is the default. Okay, so first one is, I'm going to call it as GBR for gradient boost regressor. The GBR is defined without using any of the, without altering the hyperparameters. It's a default. All right, so we have gradient boost regressor. Okay, this is the default one. I'll use another one, GBR1 is equal to, once again, the gradient boost regressor, but now you see I'm going to use various parameters such as let's define, if you remember, we have the various terms defined when we discuss in the theory part. Okay, you can go back to the theory part if you don't remember what are these parameters. One is alpha equal to, we'll keep it as 0.9, criterion, keep it mean square error, but there is what is called as a Friedman mean square error, so I'm going to use it. Friedman MSE. Okay, number of estimators, well, let's keep say 500. All right, then the max depth, want to keep it as a maybe 5 or 6, maybe, let's see. Let's go for a learning rate defined as standard 0.01, let's say, and minimum number of samples split equal to say 5. So let's train and the test with the mean square errors of both of them. All right, so what I do, I'll go with the first method, that is GBR. GBR.fit x train, training data, training labels, y train. Okay, then I go for a predict. Okay, let me run this. Y predicted is equal to GBR dot, the predict function is used to predict, so x test, pass it on to this, calculate mean square error is equal to metrics dot mean, there is a function SQ, yeah, mean squared error, it's there. So y test comma y predicted. Okay, print them MSE percentage point to floating MSE. Okay, 9.33. We'll repeat the same thing with the GBR1. Okay, so I just need this. Okay, this is GBR1.fit. Then this is y predicted 1. I also need the MSE calculated for this, so I'll call this is MSE 1 is equal to matrix of this y test 1, not y predicted 1. Okay, and then we'll ask it to print these values. MSE 1 needs to be printed. Okay, pretty much closer values. So one of the method to visualize this by looking at the actual and the predicted values of the models, right? We can definitely check that. Now let us try to visualize the actual and the predicted values in a plot for both the models that we have created. Okay, so the first one was GBR and the second model with this specified hyperparameter, that is in the GBR1. Let us try to visualize both of them. Let me create a range that is equal to the length of the testing samples. I will create a scatter plot of x versus y test as equal to 5. Okay, let me put them in the new line so that it becomes easier to understand what are the various parameters we are using. X equal to 5. Then the color, I'll specify the color as blue. Then the label is the original value. All right, so this is what is a scatter plot. Then I'll go for a plt dot plot. I'll plot the values which are actually predicted by the machine. So once again, it is x versus x is given as a name as x ax, comma the y predicted, and color is red, and give a label that is predicted. plt dot legend, and I'll also ask the plt to be shown. So the blue dots, what you see are the actual ones, and the continuously regressed values have been connected using the red color, right? So you can see that few of them are pretty much close, but there are some points like this, and you can see here. So those values have not could not be predicted. All right, so that's with respect to the first model, and I'll do the same thing with the second one. All right, so pretty much similar code. So plot the first one was a scatter, and now I'm going with the predicted value, right? So the scattered values are the true values. That's why it is original. Now you see I'm going with the y pred 1. This is the predicted value, and color is equal to red. This is a predicted. Go with the legend. Show. This was supposed to be 5. That's why I'm getting very small dots over there. Sorry. Now you can see this. Okay. All right. So those are the differences that we can observe. Okay. Do we have any doubts with this? Either put your questions in the chat box, or you are free to ask orally. Meanwhile, I'll write the heading for our next. So next we'll be checking out the implementation of the XGBoost. I'll give 2 minutes. So if you have any doubt, please let me know. All right, to implement the XGBoost, let's try to recall quickly what the XGBoost is going to do. So the gradient boosting can be optimized, right? Inside the can be optimized by using what is called as there is a Python library called XGBoost, right? Extreme gradient boosting is what is XGBoost. So gradient boosting already has been implemented. Now you can use the extreme gradient boosting. So this is actually a package, right? Which is fast, scalable, portable, and basically in when it was originally what you call when this was proposed, right, this actually won many competitions in the world of machine learning. All right, so let's try to create XGBoost regressor. All right, so that is XGB underscore regressor is equal to XGB. Already we have it in our in the system's memory. All right, so that's XGB dot XGB. Let's see whether it remembers. Yeah, XGB regressor is there. So we need to tell what is my objective. So objective is equal to it's a linear regression is what I want. I'm supposed to mention about the sample by tree by level, by node. We have various other options as well, but right now I'm using the by tree options. So for each of the tree, we'll be providing a 0 point, say 30%, 0.3. It's not tech, it's not, sorry, it is not a string. Learning rate 0.1. All right, max depth equal to 5. The alpha value, let's define that equal to 10. And the number of estimators, let's keep it to 10. Okay, we'll initialize like this, and if we expect any changes, if the output is not satisfactory, definitely we'll change it. All right. Let's split the data sets now. X train, X test, Y train, Y test. Oh, Y test should be equal to train test split X, Y, test size, say 0.2, and random stage is equal to give some number, say let's say 100. So that's how the train test splitting happens. Once it is done, now my objective is to fit this particular XGBoost regressor. So XGB underscore what is the name, rig, right? So dot, so do a fitting of this particular method. So X train and Y train. Okay, and Y, the predicted value should be equal to XGB underscore this thing dot. So you should use a predict function over here, X test. Let's run this. Now once it gets finished, okay, there's some warning. Okay, no problem, don't worry about it. So let's calculate the MSE now. So that is MSE equal to the metric dot mean squared error Y test Y predicted. I calculate the mean and I'll print it out. Okay, so that's MSE. I'll try to print it out. MSE percentage 0.2F oh, my mistake. All right, so we get a mean square error like this. So we know that in case of the the XGBoost, we can even find out what are the very important features, right? So let's try to visualize that as well. XGB dot plot underscore uh, plot underscore importance. Yeah, so we have something XGB, the regressor, and PLT dot XGB underscore PLT dot RC params figure dot fig size equal to say 7 comma 7. That's the size of the figure which I want to see. PLT dot show. It shows the important parameters. So highest importance is given to which feature, right, etc. can be done. Again, this XGBoost is a technique that can be used to identify which is your a very important feature, and feature selection can be done using this. Okay, so that is one thing that is about XGBoost, and there is another technique which is called as stacking. So overall idea of the stacking is it's again an ensemble method. We'll try to train several models with different algorithms, right? Specifically on a training data, then aggregate all the models using a different model. So the different model is called as a meta model. So you will have base learners, basic models, and obtain the results of each of these models, and using these results you train another level of another layer of learners. It's called as a meta learning models, and you make a final prediction using those outputs. So it's basically stacking. So stacking, as the name suggests, right, various what you call learners are kept one after the other. Okay. There is a stacking of uh, learners or the models. That's going to happen over here. Yeah, right. All right, so let's try to define various models as required. So before we go ahead, all right, so let me start with the XGB. XGB regressor as the first one. Then I'll go with the random forest. A random forest regressor. Number of estimators is equal to, say, I'll specify some of the parameters, all right? Max depth is equal to 5, and max features is equal to 10, let's say. Okay, then ridge is equal to ridge equal to ASO SVR with kernel is equal to F. So we have defined all the models now. Let's try to improve the results by performing what is called as a stacking. So let us try to so basically, if you understand, we need two different levels. So first level uh, is the basic level, which actually implements the learning of the input and provides some output, and those outputs are given to the next level, which actually is a meta level used for the final prediction. All right, so let me try to define the various estimator. Okay, so these are the various estimators. Then I'll do the regressor, that is equal to stacking. Stacking regressor, you just have to specify estimators equal to the same estimators we defined. I just have to say what is my final estimator underscore. Already we have defined what is XGB, it's a XG boost. So we are saying that. Then go to the regressor dot perform a fit. X train and y train. X test. Let me check what we have defined in the testing part. Let me quickly. Let's give some names to the testing data set, right? So that is X test dot columns equal to, I think we have 13 different columns, correct? So we need to define them. Let's give some names over there. Okay, so I'll give a name as a F0, F1, F2, F3, F6, F7, F10, F12. So 1, 2, 3, 4, 5, 6, 7, 13. All right. So all the 13's column names have been defined. Now I need predicted values equal to regressor dot go to the predict part, and you are supposed to perform the X test. Okay, then let's look at a score. The matrix dot, there's a R square score, correct? So R2 score, R2 underscore score, Y test, and the predicted value. Print score. Okay, so 0.84. If the R score is closer to 1, it means it's a good regression. If the R score is closer to 0, that means it is not a very good prediction, right? So because of this, as we can understand by looking at this, it's a 0.84, closer to 1. It's pretty good regression. Okay, so like that, in today's session, we have implemented 3 different types of the boosting algorithms, and we'll be looking at the cat boost algorithm in the upcoming session.